It's Friday. Well, as you can see from the screen, I figured out what was wrong with the iPad, and that was it needed to be rebooted. I didn't think you had to do that to Apple products. But it worked. As you know, Monday is Labor Day, and there is therefore no classes. Also, there's a couple of minor things we found out about Lab 1 last night. One is that, as usual, as I've said to everybody jumping up and down since the beginning of time, don't cut and paste code you don't understand. Because turning on I/O functions has real effects in the real world. Well, I did exactly that with some of Tamid's code. I cut and pasted a register definition I didn't understand, and it turns out it's CM1 con, which is the number one compare control register. And Tamid had set it to 0. So if you turn on CM1 before you zero CM1 con, guess what happens? It turns it back off again. So once again, don't cut and paste code you don't understand. The other thing is, make sure when you hook up the signal generator, I'll say this about the third time, make sure when you set up the signal generator, before you attach it to the microcontroller, make sure that the voltage does not go below 0 or above 3. Because these are unprotected inputs, or they're very gently protected inputs. And if you back bias a CMOS junction, it becomes a silicon controlled rectifier. Does anybody know what that means? It becomes a latch dead short. It's a bad thing. I decided to put together a small page called plib GCC and assembler considerations, and to put some stuff in there that I and some other people have found particularly obscure, particularly the peripheral pin select system. Oh dear, where's my pointer? Do you see it over there? Otherwise I'll have to go to a laser pointer. But the nice thing about this pointer is I can put it there and then look at you and it stays there. And with the laser pointer it would be all over the place. So, using PPS, there is a description of the PPS system which is not called that in the index, but it's in the PIC 32 reference manual, section 12.3, which has to do with I/O ports. And it describes how it's set up, describes the multiplexers and why you're limited to groups of 8 and various other features like that. But even better than that, in the MPLAB-X GUI, if you open help, and then do a search for PPS, it has all the macros explained and laid out. So when you want to do a PPS input or a PPS output, to get the syntax, the exact syntax, just use the GUI help. That's probably the easiest way to do it. But I did put examples here, again, along with the tables. So if you look at the PPS input table, there it is. Yep, group 1 is not marked as group 1. It just happens to be the first bunch of stuff above the line. And then group 2 is the next bunch of stuff. So, you do some by induction, right? I just mapped this for a while until I could figure out what was going on. But what we can see here is that slave select 1, that would be for one of the SPI channels that we'll talk about for lab 2. Slave select 1 can be mapped to any of these pins. The names, these signal names, are then, you have to separately look up to find out what pin they're on, because different packages map these signals to different pins. Oh, and I guess you can't use the C pins on our package because they don't exist. So you can use any of the A or B packages, pins. Now, another aspect of this is that RPB7, the signal RPB7, maps to the same pin as port B pin bit 7. But the I/O ports, the A and B I/O ports, are not part of the PPS. If you ask to output, if you ask to input to make port B bit 3 equal to an input, which you would do for the comparator that you need to use for lab 1, then that would be on the same pin as RPB3. So the B3 being the key feature here. Okay? That means that if you use the comparator, you can't map any of these other peripherals to RPB3. Any questions on this? This is fairly obscure. It's very powerful, very cool. Obscure. Going back a level. I put in an example here. I copied it off another page. But PPS input example, a PPS output example, and again, for reasons known only to the designers, for the input, you have the group number, then the signal name, and then the pin indicator. But for an output, you have the pin indicator, then the signal name. For lab 1, we have the example of CMP open, which requires that Cout be assigned to some pin because C1 out is on the peripheral pin select. I chose RPB9. There was some confusion in lab because the TAs who independently wrote their code chose RPB11. And so my output is on pin 18, theirs is on 21, I believe is RPB11. But when we set up port bit 3, port B bit 3 as an input, it is not part of the peripheral pin select. Instead, we're going to use mport set pins digital in bit 3. That is not remappable. That is absolutely locked to pin 7. And I copied the PLIB examples up here just for giggles. Put a little information on the XC32 compiler. Some And some of this is stuff you'd need if you wanted to write assembly language to link to C, but I found it kind of interesting. Some stuff on data types and ranges, but the thing which really got me is that integer promotion is defined in GCC such that when you do a comparison, all of these variables are promoted to full integers before the comparison. Oh, the pain. That means you get weird extensions, high bit extensions, depending on the values. Watch that. If you get comparisons that don't seem to work, look back at this page and think about integer promotion. In general, you might want to look at this page. Any questions about Lab 1? Tips on timers. Well, there's a couple of examples. If we look at proto-threads, on the proto-threads page, right after these ungainly tables, there's a section called Timers, Output Compare, PWM, and Input Capture. And the first example is a code that sets up 2 timers, 2 output compares, and an input capture. So that's probably what you want to look at. That example is probably what you want to look at for examples on how to set up timers and so on. Do you want me to get more specific on setting up timers? We can look at that code for a minute again. Down in main, for instance, we're going to set up timer 2 by turning it on, setting the source to the peripheral bus, PB. That's what source internal means. We're going to set the prescaler to 1. That means that the clock is running at the same speed as the peripheral bus. And then we give it a timeout period in ticks. And after the timeout period, it will auto reset to 0 in hardware and start counting again. You have to separately set up an interrupt if you should want it. You have to separately specify an interrupt, set it up, turn it on, give it a priority, and once you do that, it'd be a good idea to clear the interrupt flag if you care whether or not an interrupt immediately occurs. If you don't care, you don't need to clear it. In fact, I think you should probably clear it before you enable it, rather than after. Again, any questions? Is that enough on timers? Do you have some other question? Okay, yes?
In the previous page, there was a lot of code for setting up pin 7 as an input.
Yes?
In the lab, you didn't have to do that, choose the comparator?
You did not have to set up pin 7 as an input to use the comparator because input is the default for a port pin. The reset code forces all of the pins to inputs. When you actually build the code for this lab, you will remember that pin 7 is going to be changed between an input and an output dynamically, and therefore you will have to change it from input to output on every charge-discharge cycle using an input-output set command. Thank you. I was going to say that and I forgot. What else? Anybody see obscure behavior with the TFTs? Or they just kind of like worked, mostly. That's good. Saw a lot of obscure behavior with the comparator for reasons I still don't understand, aside from the CM1 con bogusness that I put into the code. At least one group had it set up completely correctly and it still didn't work. We still don't know what was wrong. We even changed out the chip in case the input was blown. My current hypothesis is magic. Actually, it's probably a bad whiteboard, but I don't know for sure. That was we got to that point at 7:30 last night, and I decided it was enough. Remember, read the whole lab. Down at the bottom of the lab, for every lab, there's a list of requirements for the lab write-up. So if we, in particular for lab 1, we scroll to the bottom here, down someplace. So we have the assignment. You will write a program that does this, blah, 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 blah. You will demonstrate, and then here are some very specific things you need to do, including a screen capture of the oscilloscope showing the charge-discharge waveform. So what happens inevitably, people will finish the lab, get all the data, and then 2 days before they have to turn in the report, they'll come back in and build the whole lab again and get that waveform and waste a bunch of time. So take the waveform while you can. Take the waveform while you're setting stuff up. Use that waveform to debug your capacitance measurement. We have cables connect to the back of the oscilloscope that hook to the computer, and then you can use the open desktop, Tektronix open desktop application to dump the image in beautiful format. If you're lazy, you can just point your cell phone at the thing and take a picture. It never comes out square and it's usually blurry, but you know, it is fast. I suggest using the USB cable. It's all cool? Let's start on lab 2. DTMF dialer. So let's look at the DTMF standard. Dual tone multi-frequency signaling with the internationally recognized touchpad here. And but this is too wordy. Let me see if I can get, where did I put the specification? Put the specification in here someplace. Oh, it's in the homework. So, specification for DTMF dialing says frequencies will vary between 697 and 1477 hertz according to the DTMF spec. All frequencies must be within 1.5 of nominal. All spurious frequencies must be lower than minus 20 dB from the main tones. How will you determine that? Scope and FFT. The scope has an FFT option on it. You press Math, FFT, and then you'll be able to measure the harmonic distortion by looking at the peaks, the height of the peaks on the oscilloscope. So you'll want a screen dump showing that your harmonic distortion is pretty good. The duration of any individual DTMF tone combination shall be not less than 65 milliseconds. Measured from the time when the tone reaches 90% of its steady state until it's dropped to 90% of its steady state. So In this particular lab, gotta love that board. In this particular lab, you're going to, does it work to right here? You're going to AM modulate this burst. So perhaps this will be 697 hertz, but it's going to ramp up over several milliseconds and then ramp down. If you just merely turn on a sine wave burst and turn it off again, it doesn't sound very nice. And why not? Because any discontinuity means higher harmonics, right? So any first order discontinuity, whoop, has a spectrum that goes as 1 over n. Any second order discontinuity in slope has a spectrum that goes over 1 over n squared. It's a good cocktail conversation to know that. And so to cut down on the harmonic distortion and to make it sound like something other than a click, you have to ramp this up. The specification is that it will ramp up over 5 milliseconds. So this ramp up period from 0 to 90% will be 5 milliseconds. And then from 90% or so back down will be another 5 milliseconds. And this part has to be a minimum of 65 milliseconds. From 90 to 90. Duration of the pause between any individual DTMF tone combination will not be less than 65 milliseconds, measured from the time when the tone has dropped from 10% of its steady state until it's risen to 10% of its steady state in the next burst. Yes?
All these percentages are relative to like the envelope of the signal, right?
Are relative to the maximum intensity. Yes, the envelope. Clearly, you can make life easier on yourself if you don't try and make the fastest possible signaling. You can avoid a lot of sort of duration arithmetic if you just say, okay, I'm going to make the whole thing 65 plus 5 plus 5. I'll just make it 75 milliseconds from the time it starts to the time it ends. Or make it 100 milliseconds. That's greater than 65. It's legal. And then the usual annoying questions. What direct digital sample frequency is required? Well, that's actually tricky. But I won't make you answer it right now. But it's bigger than the Nyquist frequency. Should you add low pass? I don't know. Maybe you should. How accurate is the internal oscillator? The usual kind of questions. So now let's go back and look at the DTMF dialing frequency, actual frequencies. So we'll go back to lab 2. There's a table down here. So when you press the button 1, you get a combination, a linear combination of equal amplitude of 697 hertz and 1209 hertz. And these are specifically chosen to be anharmonic. They are not particularly related harmonically, and so it is hard for human voices to generate the tone pair. Each one of these frequencies will have to be accurate within 1.5%. To prove that, now you're going to have a keypad, a 12-key keypad. When you press a button, you'll hear the tone pair. But to calibrate this, what you're going to do is have a test mode. You hold down a special button someplace, and in test mode, when you press the button 1, you get frequency 1. When you press the button 2, you get frequency 2, so that you can read them using the oscilloscope frequency meter. So there'll be two modes. There'll be the normal DTMF dialing where you press 1 and you'll get these two tones equally in amplitude, or the test mode where you press 1 and you get this, and you press 7 and you get this one. Furthermore, as you press the buttons, the numbers that have been pressed will be accumulated in a string or an array, however you want to think of it, up to 12 digits, so that then when you press dial, it plays back the whole string of 10 or 12 or however many digits you have, while meeting the timing spec for DTMF dialing. Some years I've had people speak the digits rather than play the tones. So when you press 1, it has to say 1 in a suitably robotic voice. And I'll do that some other year, but not this year. This is my guess for the possible pin assignments that you're going to need. TFT will still be used for display, for debugging. The keypad needs 7 I/O lines. We'll talk about that in much more detail. And then the DAC, the digital analog converter, is going to be an SPI device that uses another SPI channel. The TFT uses SPI1. We're going to use SPI2 to control the DAC. One little feature of this that's very necessary is you're going to have to debounce the keypad. And the reason for that is that mechanical buttons are spring mass systems. And so they oscillate. In fact, when you press on a button, so let's say you press right here, ideally, the logic level would go high and stay high. This being the CMOS transition voltage from 0 to 1. And what you will find is that any button will, when you press it, will have a little bit of a lag time, but it may bounce for a few cycles before it stabilizes. And the bounce time here this total time might be 5 milliseconds, so one bounce period might be 500 microseconds. Well, geez, that's several thousand machine cycles. And so if all you're doing is saying, is the button down, is the button down, is the button up, is the button down, you're going to report, when you press 1, you're going to repress, the user pressed 1 3 times. 1, 1, 1. Because it crossed the CMOS threshold 3 times. So, if your cell phone did that, when you were trying to dial 607, you got 666-000-775, you'd drop it on the ground and stand on it. So you have to debounce. There has to be a state machine that you're going to build that is going to not process a push until the push is stable, and it is not going to process another push until the release is stable, because on the release you also get oscillation. So you're going to have to debounce the push and the release. It means that usually a 4-state state machine is pretty is pretty safe, and we'll talk about that too. Some detail. The star button erases the entire stored number. When the pound button is pressed, the DTMF signal for each entered digit will play. So you have like speed dial. Yes?
Can we use hardware to debounce? Like put a capacitor in there or something?
It's not good enough.
Okay.
Yes, the obsessive will do that. If you want to debounce completely in hardware, you need a capacitor and a Schmidt trigger. Don't do that. Just use software. So you're going to need a method for producing precision sine waves, precision frequency. You're going to need a method for scaling them because you have to add them. The output is going to be a 12-bit DAC signal. You're going to need a scheme for amplitude modulating the waveform. So you'll have to have a start time, a duration, and an end time that you're keeping track of in some state machine to make the burst. And of course you're going to want images of all of these things. Scope captures of all of the waveforms. Any questions on this? So the I tried to lay out the system like this. I found it nicer to put the keypad near to the CPU because it required 7 wires running to it, whereas the TFT only required 7, 6. But lay it out any way you want. And as another sort of gotcha, I originally had 16 keypads, which I prefer because you have the 10 keys plus now 6 function keys that you can use. But it turns out the price differential between 16 key and 12 key is a factor of 3. Why would that be? No idea? Exactly. Nobody buys 16 keys in this, so there's no scale of production and there's no surplus market. So, I mean, when's the last time you saw a phone that had an ABCD on it, right? Somebody's going to say their smartphone does. So, for historical reasons, I still have a pile of these 16-key keyboards. If somebody wants to use one, there are actually 3 generations. There's the top 8 pin, the top 9 pin, the bottom 8 pin, and then the 12 key. But the 12 key is what most people are going to use, what I recommend that you use. For row 1 is 1, 2, 3. Row 2 is 4, 5, 6. Column 2 is 2, 5, 8, 0. The way I hook this up, but you don't have to, is to use 4 8-port pins for the rows because because they're all in the same port, I could drive them simultaneously as the 4 lower bits of a word. And then read the 3 B port pins simultaneously because you can read the whole B port at once. The internal structure of the keypad is boringly simple. It is an array of 4 wires by 3 wires with a switch connecting every intersection. So when all the switches are open, when you're not touching the keypad, and you run those points to B7, B8, and B9, unless you have a pull-down resistor or a pull-up resistor attached to the port pin will float. If you have an unterminated input on this architecture, CMOS input, 10 to the 11th ohms, air, what's the impedance of air? It's lower than that. That means that whatever the voltage in the air around the terminal lead is will be the voltage on the pin, except it's clipped by a pair of diodes on the input to 0 to 3.3 volts. In other words, it may as well be a random value. So unterminated inputs are a logical hazard. They will kill your code because you can never predict what the input is going to be. So the first version of this I added 10K resistors externally because I couldn't figure out how to turn on the internal pull downs. After I asked Hamid where the documentation was, he said, oh, well, that's on page 104. There's one line on page 144 of the data sheet. I went, oh. I looked there, and yes, indeed, there was one line which gave me the name of the register. Then you could do a search and find the bit pattern to set the register. But there are internal pull downs and internal pull ups. They have some value between 10K and 100K, and you don't care. I would suggest turning on the internal pull downs and avoiding having these resistors here. There's a test code where I didn't know yet how to turn on the pull downs, so I added a line here. If you set the CNPDB register, that's the change notification pull down bit register. What the hell does that mean? To bit 7, bit 8, bit 9, it turns on the change notification pull down port B 7, 8, and 9. That was obscure enough that I wrote a macro that looks like the other plib macros, but was never written by anybody. Probably because that intern failed to show up. So, enable pull down, so I wrote these, enable pull down B bits does 2 things. It does a CNPUB clear, that turns off the pull-up resistor, and then does a CNPDB set, the pull-down resistors. And the clear and set registers are separate registers that take a bit mask to do their operation. So this sets only the bits you specify. In other words, 7, 8, and 9. So I just wrote these all out. They're probably all correct, but I only tested that one. You know what that means? Yeah. So then if you include these macros, you can just write enable pull down B bit 7, 8, 9. And then you don't have to add the 10K resistors. Any questions on this? Yes?
So we only need the pull-down resistors for the columns, not the...
So what you're going to do is you're going to drive A0 through A3 as outputs. So these are going to be outputs, these are going to be inputs. And the pattern is going to be put a pulse on A0, make these all 0. Put a 1 on A0, make these all 0. Turn that off, put a 1 on A1, make the rest 0. Then turn that off, put a 1 on A2. So you're going to scan this way and read this way. That is why there are 300 ohm resistors on every line. What if there weren't 300 ohm resistors on every line? Then you press a button, it works. You press 2 buttons on different rows. You press 1 and 4, and you have a short from A0 through here back to A1, and one of the port pins destroys itself. So these are necessary. These are not optional in this case. This is not just a good idea, it's required due to the nature of this. How could you do that differently if you wanted to be even more obsessively safe? Diodes. Good. Put a diode on each one of these and only drive it when it's high. It turns out the resistors have an interesting side effect. And that is, if you push 2 buttons, the voltage you get out is only VCC over 2, and it doesn't register as a logic 1. And so having the resistors, rather, I was going to change these out for diodes and said, wait a minute, this works better because of the cheesiness. And I'll explain that more when we get around to talking about the keypad scanner in some detail. So, you're going to write a keypad scanner. I actually wrote one for you, but you're going to probably hack on it to make it into a function. The keyboard debounce state machine is going to repeatedly call the keypad scanner every 30 milliseconds or so. On the basis of the scanned keypad, or on the basis of the keypad state machine, then you're going to decide whether you should play a tone or play back all 10 or 12 tones. And I think there's one other function. I think that the star key has to be able to erase the array, zero the array, so that you can dial a new number. Yeah, okay. Oh. Again, any questions? So leave the TFT hooked up. Don't disconnect it. You may have to move it so everything fits on the same whiteboard, because this gets tedious if you start using multiple whiteboards. They don't fit in the box. We use up all the whiteboards, various things like that. So rearrange the code, or rearrange the hardware so that everything fits on one board nicely and neatly. And that'll be the first step. Any questions? I'll start in on keypad scanning next time. Are there any questions about write-ups or anything of that sort? Logistical questions? Final projects. All right. We got some time for final projects. So, I presume that at this point, most of you have looked at the final projects page. How many people have actually looked at the final projects page? Wow, that's amazing. I wonder where all those hits came from on YouTube. I thought it was from this class, because it happened to occur starting at the beginning of the week. So somebody else must have decided to look at the page. So we look at one of the projects from last semester. In this case, it was a real-time scrolling spectrograph. Slowly it loads. And they used, this is, oh man, that is the, let's go Skittle sorter. Now so I was looking for one of the pages that, yeah, this was pretty amazing because the whole thing was made out of cardboard. Every single mechanical component. That's, does anybody recognize what that is?
Oil funnel?
It's a what?
Oil funnel?
Yeah, in fact, it's a transmission fluid funnel. It's close enough, yeah. And so they built a Skittle sorter. But what I was looking for is the standard Cornell format. There we go. This one looks like every other Cornell page. This is what many people use as a template that I, like everybody else, downloaded from CIT. And I'm asking people to do a soundbite. You should be able to say in 9 seconds what your project is about. One sentence. First thing to work on is the soundbite. If you can't describe in one sentence what you're trying to build, you don't know what you're trying to build. And of course, we want people to put their names on it. You'll be amazed at how many people forget to put their names on their web page. I actually recommend not putting net IDs on the web page, however, because you will be astonished at the amount of mail you get. Some of it really incomprehensible. And some of it annoying, like, will you do my project for me? No exaggeration. So, typical layout. Let's see. So, I get the final project is written as a web page. There is no other documentation. This is part of your liberal arts education, is to learn how to do a web page. Just like 25 years ago I would have said, you have to type the report. Now you have to do a web page. You can elect not to have it linked on the class website. You do not have to have it linked. It does not have to be public. But you have to write it and give it to us. If you specify in the email, the transference email, that you don't want it linked, I won't link it. But we have to be able to look at it as a web page. You can make a really ugly web page by writing everything as a Word document and then saying save as HTML. That makes a good-looking web page as long as the person viewing it is using Internet Explorer. And anything else is just horribly ugly because every special character that's embedded by Word turns into a question mark. And that's about 100 per page. So if you're pressed for time and you can't figure out what else to do, you do that, and then you come back and fix it later when you're embarrassed. But the way that seems to be the most effective is to download a copy of Dreamweaver, which I believe has a 30-day free license. So don't download it until near the time of the final project. And you can use it for 30 days, get the thing turned out, and then delete it. Dreamweaver is a WYSIWYG editor for web pages. What is not acceptable is to use a site like Wix, W-I-X, which writes web pages for you. You must submit this as an HTML file to live on our server. Question? Yeah. No. See the line? That's what everybody asks, and that's why the line here says the project numbers are for identification and do not represent ranking. They are actually in the order in which they're submitted, with very minor reordering to make things that are similar together. So for instance, one year, I don't know why, 2 people did a saxophone synthesizer, full size, you played it like this, one out of PVC pipe, it's hilarious, and the other one out of foam core. And I moved those until they were together because it was pretty obvious they were related. Right. So I do some minor reordering, but it's not related to, particularly to quality. Any questions on this? Let's get out of here.